Good morning or good afternoon to everybody. Thank you for logging into our webinar today. My name is Rhys Lewis, and you'll see my picture on the bottom right-hand side of our screen, but we're also joined today by our technical guru, Peter Debney, who you'll be introduced to in a few slides' time. So today we're going to look at some of the solutions we have available to you for concrete analysis and design. Some of them are ADC, ADSEC, and GSA building, which may be products that you already use or are interested in understanding more about. So at this point, I'll hand over to Peter to get into the nuts and bolts of the webinar today and why you've all actually logged in. So Peter, I'll hand over to you now, if that's okay.
Thank you very much, Rhys. Oh, I'm on the wrong slide. Oh, there we go. Excellent. Thank you very much. So, let's look at some of these programs in more detail. So there are three programs: ADC, ADSEC, and GSA. We'll start with the easiest one, ADC, which is a simple component level concrete design program. So what it does is beam, slabs, and columns. Beams and slabs, you give the reinforcements. Well, you give the loads and the dimensions. It'll give the reinforcements, and similarly, if your columns, you give the loads. It will give you the reinforcement. It will give you the reinforcement choices that you can take to achieve your design. It covers a wide range of international codes, but the best way to think is to see ADC in action. So let me just go and open up ADC, and I'll just show you putting together a couple of analyses. Now, I'll do beams first of all. Now, there are the slabs, rib slabs and solid slabs there as well. In principle, they're pretty much the same as beam design, so I won't show you both of those because there'll be a lot of repetition. But first of all, we'll set our design codes. I'll go with Eurocodes GB, but you got the American options, Australian, the British code, Hong Kong, Indian, and so on. I'll set number of spans. Now, in this wizard will be setting a number of parameters. Everything can be adjusted after you've launched the model properly, apart from number of spans. Number of spans is fixed for the beams and slabs. Everything else is adjustable. So, as I said, everything is adjustable. So I'll just set in an initial default span length. I'll say the section is going to be a choice of these five: rectangular, T, taper, general iron, general taper T. I'll go for a taper T. So a tapering beam, but takes into account some slab. So overall, say 500 deep, a meter wide. How thick is the slab? How wide is the beam at the top? Oops. And how wide is the beam at the bottom? And there is our section. Now for supports, we could take simple supports, they're just pin supports, or I'm going to take some columns supports because these will give some moment stiffness, and I'll add in some, let's say, some rectangular columns, 300 square, just to match the bottom of the beam. 3 meters to the next floor, and I'll copy that either side. So we've got 2 sets, but let's say the bottom was 3.5, and you can adjust these. The end supports, they can pick up these columns, or we could say make one end a cantilever and the other end a fully fixed, say it's connecting into the end of a concrete wall or something like that. Other settings in here: general specification, things like load cases, redistribution, various checks, self-weight included, that sort of thing. But also there's a material specification, which is definitely worth setting because this gives you your concrete grades and your reinforcement grades. Note that these grades are based on the code that you're using. If the grade you want to use is not there, it's probably because it's from a different code. We have found this a few times with people wanting to use Eurocode design with old 8110 grades. The two are not fully compatible. Next, loading, general loading. Let's say 18 dead, 9 live. You could set it to just a single span, but I'll set all spans. You can adjust these individually afterwards. Self-weight calculation. Redistribution. I'll leave redistribution off. I was always taught as a young graduate to leave redistribution in your back pocket until the beams and bars are on site and you realise that you've forgotten to do something. And redistribution just gives you that extra little bit of factor of safety to help you with those difficult spots. Cover. You can set the covers, and there is a cover code, and you can go in and set your exposure class or whatever to set the cover on the concrete automatically, which then can be overridden individually. Sizes and limits. This enables you to take some default bar sizes. We can add in our own bar sizes. We then set where we actually want to use these bars as options, and let's say 10 to 12 mil links and 16 continuities and so on. So ADC won't try to use 16s or even 50s for links, and it won't try to use 8 mils for main bars, and that's something. So you can control the results that are coming out. Spacing is all about the detailing requirements. Can the poker get into the beam? Other minimum clear distances and so on between bars. Selection criteria. This varies depending on the beam shape that you're chosen. I've asked for trapezoidal beam, therefore it's given me a choice between trapezoidal and rectangular links, and so on. So let's look at this, and there is our section. At the moment we've got quite a large cantilever, which is 6 meters, and there are our sections. So let's adjust the span geometry there, and let's run the wizard on this and say I'm going to span length only 1.5 meters, and for the section I'm going to change that to just a taper, and so it was 500 deep, 400 wide, 300 at the bottom. And so there is our second span, first span, and so on. So we've also got the loads on here. So if we analyze this, let me switch those off, and we can get the shear forces, but let's look at the bending moments. You can see from the bending moments, we ATC has taken into account patch loadings, which are specified here in the prescribed load cases, but you can also set your own user-defined load cases. You can also see that the column stiffnesses have been modifying the peak bending moments as well. That's just the bending moments. Let's look at the reinforcements. If I click on the design, ADC will calculate the best bars to go into the beams, and there's both the longitudinal and the shear links. If we zoom in on one of these sections, you can see the main top and bottom bars, the continuity bars, and so on, and the cross sections through, showing where the bars go. You can print out these screens. You can also print out text which shows in more detail the bars which are going in for some of your calculations and so on. Slabs are similar. Columns are a little bit different. Let me just close these a bit. Let's start with a new model which does columns. So for columns, same list of codes, but I'm going to use a column design. Now columns, for column you only do a floor-to-floor design. You don't do multiple spans of columns, but you do get things like automatic calculation of eccentric moments from second order effects and so on, as you see there. So you don't have to remember to add those moments in. They will happen automatically unless you want to override them. Sections, rectangular or circular. I'll go for circular. ADC is very popular with our piling designers, customers. I'll go for a 450 diameter. Concrete grades, reinforcement grades, effective lengths. So let's say it's going to be like that. I'll say yeah, it's a 4 meter clear in the other direction. It's circular. It's going to be symmetrical. And so we can use these standard effective lengths or slenderness options, or you can click on this tab here and you can go in and set these manually yourself. Let's go with those, I think. Axial force. I'll put an axial force. I won't bother with moments because when we look at the results, we can see these are added in automatically. Size and limits. These are the same restrictions as before, slightly different. Choices. Bar arrangement. Now the bar arrangement, because these are columns, if it's a circular column, you're given a choice of one or more rings of bars with, I've got a choice of 6, 8, 10 or 12 bars. If it was a rectangular section, you'd be given the choice of where the bars go in slightly more detail. Cover says for, assuming this is a pile, I'll just put in 75mm cover. And the checks, again, detailing checks, spacing and so on. So there is our column section, and whilst there are about 70 odd possible sections, ADC says there's only about 12 which are actually suitable, which actually meet the detailing checks. If we now analyze this or design this, you see 4 of these have insufficient capacity. Note that we put no bending moment on, but they've failed in bending because of the eccentric loads. And if you look in detail at the results and scroll down to the bottom, we can see that there are 4 sections there in red. These have failed. A number of sections in black. These are okay. And 1 section in blue, which is the one with the lowest quantity of reinforcement. That's running at 96% efficiency. So that's section 31, which is this one here. But we don't have to take that out. We could take section 33 or 35. Let's go with 31. If we look at some of the graphical results, if we say look at the axial moment chart for this, you can see that the applied load of 3000 kilonewtons, remember we applied no moment, but it's calculated the moment requirement is, or actual load is about 75 or so, 80 kilonewton meters due to the second order effects. Now these charts here, this chart here and this moment interaction chart, these are all coming from our ADSEC ADC uses ADSEC to help it calculate these section capacities. Now, AdSec is also available as a standalone program, and whilst it does of everything that ADC requires, it can also do an awful lot more, because AdSec is not just a reinforced concrete analysis program. It also does composite columns, concrete encasement, concrete filling, and so on. FRP materials, so carbon fiber plates on existing beams, GRP reinforcement, etc., etc. The sections themselves can be simple or they can be complex. ADC only does simple sections. AdSec will do any section you want. The section on the right is an example from the Washington Air Force Memorial. Not just a triangular reinforced section, but also composite with the stainless steel cladding as well. Results: these axial moment charts, as we saw in ADC, the moment charts for a range of axial loads. Also, interesting one, the moment stiffness chart. So this is plotting the stiffness of the section over a range of bending moments up to failure for a number of given axial loads. Output this is the EI, or the stiffness, and this can then be fed into GSA for your for more accurate concrete deflections. Apart from these charts, from AdSec you also get calculations like serviceability, crack widths, and the calculations are to all these international codes from wherever you need them. So AdSec in detail. Let's what I'm going to do is I'm going to put together a simple AdSec section to begin with, just a rectangular beam, and again I'll use the Eurocode UK Annex. I'm going to say I could take concrete, I could take steel section, I could take FRP. I'm just looking at concrete today, and the section, again, this is a single wizard, many more choices, plus the perimeter section. I'll come back to the perimeter section, but all these parametric sections I'll take rectangular. Let's say 600D, 400 wide. Aggregate size for checks on bar spacings and so on. And then, whilst I could add in lines and arcs and so on of bars and put pre-stresses on, what I'm actually going to do is I'm going to use a template. Let's say it's a beam arrangement. Cover, use it as before. Links. Now the links are there not for shear calculation because it's purely a cross-section analysis. So the links are there to position the main bars. So top and bottom bars, let's say 3 T12s at the top and 4 T25s at the bottom. These bars can also be paired as well. It's a reasonably deep beam, 2 feet deep. Let's put on a sidebar 16 diameter. And there is our section. Now, AdSec can work, just section calculations. So I'll just take the axial moment chart. And note that's worth calculating. It doesn't just take into account the bottom bars, but top bars and side bars as well. Admittedly, the side bars will be quite close to the neutral axis. They won't be doing very much, but unless of course we take the minor axis calculation, in which case the side bars will be doing a reasonable amount. Right, let me just set that back a minute. tuck that up in the corner. Another chart, the moment chart. Note that this is a beam, but it's got an axial capacity of just over 4,000. So if I say axial loads of 0 to 4,000, step 1,000 kilonewtons. And you see the different rings, different colored rings, are for different axial loads, and you can then see where your moments fall on this. Third chart I mentioned is the moment curvature, and again it's based on the axial load, so 0 to 4,000 step 1,000. Take into account long-term or short-term loads and so on, so let's just run that for long-term loads. Let's calculate a note for those, and there we have the EI, the stiffness of the section, against a range of bending moments for a number of axial loads. To extract these figures, you can right-click and say cursor toolkit coordinates of nearest point, and so we can see that point there, 120 kilonewtons, 69817 kilonewton meters EI value. Or you could, in the output view, ask for the chart details. And of course, if I just go back to here and fire up Excel, if I right-click and copy those points, I can then paste those values into there, and you can then use Excel to extrapolate between the values, create your own graphs, and so on. So that's general analysis, but let's actually put some loads in. So I'm going to create some load case titles, being old fashioned, call them dead and alive. Close off those output views. And then some loading. I'll say section force, can do some other loading types. No axial loads, let's say 200 kilonewtons dead load. And the second load case, 100 kilonewtons live load, or imposed load, or variable load, depending on which code you're using. We'll then tell AdTech what calculations you want to do with that. So a ULS, ultimate limit state, I'm going to say 1.35 L1 plus 1.5 L2. Or there's the serviceability limit state case, where I just say imposed loads. Cracking from the imposed loads, I'm not interested in the cracking from the dead loads and so on. So let's run these. So I mentioned cracking. Let's use serviceability limit state first. General results, cracking results over the side there. The results you get for that load case includes the moments and strain planes, the stresses and strains in the bars and the reinforcements, and down there at the bottom the crack width calculations, which you can see, there it is, for the two worst case bars. In this case, both bars are coming out with a crack width of 0.07 millimeters, which is fine by me. We also have two ultimate limit state checks. There's ULS loads. Now, ULS loads says, is the section strong enough? And if you get a result, it is strong enough. And you then get the stresses and strains for those loads. ULS strength is slightly different, so that's looking at how strong the section is. And so you now see with the ULS strength, you get an M over MU, an MU calculation, a moment capacity calculation for that given axial load, and hence a utilization factor. So this is beam is running at 91% at the moment. Note that the stresses and strains in the section and rebar for ULS strength are based on the MU, the ultimate capacity, not the applied load. So there will be slightly different results to the ULS loads. That's a simple section. You can also do something a bit more interesting. Let me just type another model in there. And this time, rather than taking one of these parametric sections, I'm going to take a perimeter. Now, perimeter, you define the corner coordinates of the section, and you can specify the coordinates manually. We have a number of bridge beams which you can set, or you can import a DXF file. Here's one I prepared earlier, which is a core wall, and let's centralize the centroid in that, and you can see the coordinates forming the closed loop. Now, there's no template reinforcement option for this because it's a non-standard shape, but we do have tools such as this one here, add perimeter bars, which we then say, okay, we've got our cover requirements. Links, well, these could be links, these could be horizontal laces. Like I say, we've got 12mm horizontal bars with the verticals on the inside, and the vertical bars are going to be 16s at 200. And you see, AddSec then calculates where the bars need to go around the section, so you don't have to do all that working out the details of all these lines of bars. And you can then calculate this in the same way that you do with the earlier section. I mentioned about the moment stiffness charts and values feeding into GSA. So GSA is our structural analysis program. It actually comes in 4 versions. I mentioned GSA building at the beginning. GSA building is the most common program version used for analyzing concrete with. There are 3 in fact. There's GSA analysis, which is just analysis. This is the one version which does not include the concrete design, but the other 3 do. So bridges, aimed at bridge designers, includes concrete design along with the bridge load optimization and footfall and so on. There's the building, steel and concrete design, footfall analysis, soil structure interaction, and then there's GSA Suite, which is absolutely everything. Now, we could talk all week on GSA, but the crucial thing we're looking at today is the RC slab aspect of GSA. So what the concrete design in GSA does is it takes the 2D element results and then works out the bending moment, the requirements of the reinforcement based on the bending moments and the in-plane forces and torsion and all those sorts of things. Again, to the variety of codes. So let's look at GSA. And to save time, I'm going to grab a model that I prepared earlier. This model, number of constants, a flat slab. I've included the loads in here, and you note under the permanent loads, dead loads, I've got a line load around the edge. This, if I zoom in, switch the nodes on, shrink elements, this is achieved by running a string of bar elements around the edge. These bars have negligible cross-section. Of course, being bars, they have no bending stiffness, but this means they're quite suitable for applying a UDL onto, which then distributes onto the slab, and their section is such that they don't contribute stiffness, or at least not stiffness that you'd notice to the overall analysis. I've also, if I switch on the column outlines, you see we've got the columns, and I've modeled the column outlines in the slab here as well, and that includes a rigid constraint between the centroid of the column to the face of the column. This is to prevent those unrealistic peak moments you'll get at the point support on the mesh of 2D elements. You may still get a slight discontinuity and so on around the edge, but it avoids those peaks which don't happen in real life. So for the analysis for this, that's all set up ready to go. Let me just analyze that. And so we now have switch off the bar displacements. Rescale that. So we got dead load deflections and live load deflections, and so on, which we can contour, of course. But what we want is the concrete design, so this would be the ultimate load. So let me go and define an ultimate limit state case, which is going to be, well, no, load case 1 is dead, load case 2 is live, so a permanent variable. So displacement is not appropriate now, but you do get max and min moments, etc., out of this analysis. We haven't got the reinforcement yet, so let's go and specify the design code. So design specification, concrete code, Eurocode, UK Annex. And under the design properties, design RC slab design properties, you can use just this table, but it's best if you use the wizard, because you're going to get a few additional options. So concrete grade, reinforcement grades, direction of reinforcement. Note this is relative to the local x-axis of the elements, and because the elements in this model are defined by the global axis, the local x is parallel to the global x. So local x is going left to right. Direction A, direction B is going more sort of up and down direction. Because the RC slab calculation is not calculating bar sizes but bar areas required, you don't put in cover, you put in the axis to surface distance of the reinforcement. So you've got to make a guess as to what bar sizes you're going to be using or like to be using, and therefore set these values accordingly. You can also set the minimum areas of reinforcement. Generally, I would do that if you're doing the design properly. I will leave these off because then you'll see a few more contours, and you won't just get a mass of minimum steel. If you wish, you can override the analysis thickness. These have been modelled in as 300 thick. You can get after analysis say, actually, let's just try at T75 or whatever, and see how that affects the reinforcements. So you can quickly adjust the design without having to reanalyze each time. Talking about minimum areas of steel, we can also set in minimum areas of compression reinforcement if we wish. So that's set. So the design appears under the contours, and we see we've got the top A, X direction, top B, Y direction, bottom A, bottom B, and these calculations, which I'll run now, these calculations are all based on the full wood alma moments plus in-plane forces, so it's perfectly suitable for both core walls and flat slabs. Top bars in the B direction, bottom in the A, bottom in the B. So you can see then where the bars are going to be required, and you can then rationalize these. Now you rationalize them maybe by saving the image out and then importing it into, say, AutoCAD or some other CAD program as a background. Or if you wanted to print this out, let me just set it up as landscape. If you print it out, well, if you're a color printer set, right, if you've got black and white printers like I've got at the moment, that's getting a bit difficult to write on. So what I'll do is go and set my line contours to lines, and then that's then a lot easier to write on. Note the scale as well. Let me just double click on the screen, ask for an engineering scale, and so that's now 1 to 200. So you can scale off this printout now. Right. So that is a very quick whistle-stop tour around the 3 concrete design programs. We've only dipped our toes into them, so there. So if you've got any questions, do please ask away, and we can look at things in more detail for you.